Welcome back to Decouple. Today I'm joined by Tony Roulstone. Tony is a business consultant and lecturer in nuclear engineering at the University of Cambridge. He has worked on fast reactor development and spent 20 years with Rolls Royce as an engineer in nuclear submarine propulsion and later as the engineering director. For his final period at Rolls Royce, Tony led an ambitious business efficiency and change program for the whole company, covering aerospace and industrial power groups in the UK, US, and around the world. Tony, it's a pleasure having you here on Decouple. Thank you for making the time.
Look forward to it.
So, Tony, I'd like to get a little bit of a more personal self-introduction from my guests. So tell me a little bit more about what drew you into this field, some kind of interesting personal anecdote that can make you relatable to our guests here.
I was involved at Rolls Royce, involved in nuclear submarines, are somewhat different, but, being the company I was involved in and led at the end has built 30 nuclear reactors over the last 50 years and refueled them and supported them. And so they know quite a lot about building nuclear reactors, and they know about the business about production engineering, but generally they were built in groups of identical reactors, sometimes 4 and sometimes 7. Related to classes of submarines. So that this background in manufacturing and also a background in nuclear is not something that everybody has. Most nuclear engineers have been involved in 1 or 2 very large civil projects, and they know that's their experience range. The last 10 years I've been back at the University of Cambridge. I went back when he said we're going to have a nuclear renaissance in 2011 to design and start up and run a course called Educating the Nuclear Leaders of Tomorrow, a master's course in nuclear energy. And this led me into a number of things, which in the way of things, master's students were always teaching you stuff, and they got me into SMRs, and I had to learn a lot to catch up with them, and this got me involved in research. And we've had a couple of PhD students working over the last 5 years in this area. And the business about economics and safety of small reactors is really my field now.
It's pretty painful to hear the phrase the nuclear renaissance of the 2010, 2011. It's been interesting as I kind of dive deeper into this topic, looking at those heady times of the early 2000s when there was a lot of optimism around new designs like the EP1000 or the EPR and seemingly big plans for them. Obviously, Fukushima threw some cold water on them, not to make too bad of a pun there. But also the buildouts have been sort of radically unsuccessful for a variety of reasons, it sounds like. And I'm looking forward to delving into that. Perhaps as a good place to start, I've been sort of using this term of the kind of the secret sauce of a successful nuclear buildout. So we're trying to talk about, remixing that sauce again, and perhaps that's going to be based on an SMR strategy. But let's kind of reach back a little bit historically, and I'm not sure if you can provide a little bit of an overview for what made previous buildouts successful, like say France or South Korea or Japan, where nuclear really was looking cost competitive.
Well, I will come on to France and Korea, but one of the things that's forgotten actually is the source, the secret of success existed in the US in the 1970s when Westinghouse and Bechtel built about 20 or 25 3-loop PWRs. And they were so successful that Congress thought they were ripping the people off. And they said that they broke this cartel up. And they said, no, you must have, you can't have an architect, engineer, and a vendor all tied together in this way. You need to diversify. And as a result of that you now had, in the later period, the late 1970s and the 1980s, you had 5 nuclear vendors, and you had lots of different architect engineers, some of them who had built nuclear power stations before and some who didn't. And you had local states designs and local state variations. And we had this almost Chinese thing, 1,000 flowers blossom, but you end up great diversity. And so almost no 2 nuclear power plants in the States these days are the same. And of course, this was exacerbated because after 3 Mile Island, there was lots of on-plant changes and changes while people were building plants. and you end up this incredible mix where there's almost no two plants are the same. The nearest ones I always say are the Diablo Canyon in California, where they were going to build more, but they built two pretty well the same. So the best data on nuclear power is in the US, published data, but it's also always confusing because of this diversity, the lack of standardization and such like. And so you look to other countries. There's been good work done in many countries, and the UK bit of it's been done by the Energy Technology Institute, and MIT have looked at the same things, and French have also looked at it. That basically where people have standardized and thought about the production engineering, you need to do these things together. Only when you build one and then two and then three that are similar, it is worth the effort of thinking about the production engineering of these things. And of course, the French, they took a license from Westinghouse in the early 1970s, and they built 24 3-loop 900 megawatt plants, very similar. There were some slight changes in that, and then they made those into 4-loop plants, which is 1,200 megawatts. So all the other components were the same, but the main vessel and the reactor core was slightly different. And they built 30 of those. So they have 54, and they built them quite quickly as well. So between completing the first one, I think in 1977, and the last of the 1200s in about 1990, so over 13 years, they built 54 reactors. That's amazing. And they did it because they had a license from the US, they had Westinghouse help, Bechtel were involved, and EDF in the center of this, who are very good at operating and learned how to be very good at building it, had central control of the design, although the individual contractors in different places were farmed out, and they stopped design proliferations, and where there were design improvements, they made sure those were released in echelon so that there was good control. And as a result, they built very, by our terms, very, even when you inflate it and you think about all these other things, they were very economical power plants. And one of the little ironies of life is the UK in 2010-11 had an ambitious plan to build about 16 gigawatts of nuclear power plant. And the case was based on this data from France. But actually, they had a strategy of building it with a number of designs and a number of different utilities and a number of different vendors, which was completely counter what was delivered. More recently than the 1990s, the Japanese who were building their own variants of PWRs and BWRs from the US, Toshiba and Hitachi and such like, they thought about in their very methodical way, they thought about the great expense of building these reactors, and they started a program of improvement, simple improvement. There's a Hitachi approach had 4 parts: a design standardization and a big CAD model, so they captured and controlled the design. In the past or in other places, the top level design is detailed about the reactor vessel and the core and pumps, but it's almost a sketch design of the rest of the plant. They indicate where the cables might run and what the thickness of concrete might be, but actually it's up to the contractor to do the detailed design. And what Hitachi did with their first part is they captured huge amounts of the design, so they had it under control. And when they built another one, they knew what it was like, and they had it designed before it was being built. And the second part of it is they decided to make a bit of on-site modularization. They made some quite big modules, 500 and 600 tons, and then they got some big cranes and put those in place. And the fourth element was they realized this is a craft business, building nuclear power stations. They're very complicated. It requires on all the skills of welding and electricians and piping engineers and such like. The skill level of those engineers on site was important, and they worked on upskilling people, retaining people, moving them from site to site. And the result, over a number of years, they got about a 40% productivity improvement from site labor. At the same time as those ideas were going on, Korea with a national program, which is smaller than, but very much matched on the French program. It took a license from Combustion Engineering, later bought by Westinghouse, on a design called Combustion System 80. And they built a couple of System 80s, and then they made some of it indigenous, and they built their own versions of it, and then they built a slightly bigger one, but still the same thing. And they built it on a small number of sites, so the learning from one site to the other was retained. And they had a national program of one utility, one contractor, main contractor, and a central repository of knowledge, a very, very big drive, and of course central funding for what was quite a big program. And they built about one a year for 10 or 15 years, and they actually brought the cost in real terms of later reactors down quite substantially. Probably the best documented data in the world. And to some extent, the Chinese, because they're nearby, have been looking over their shoulder and emulating some of these best practices from Japan and Korea. And more recently, they've been building standardized reactors, and they've been building them quite rapidly. That is a few a year. And they are now have world-leading productivity and short build timescales, which are a very good indication of productivity. So that's the sort of the general position. I mean, the background, Russia has been building reactors, but the information from Russia is always very cloaked in darkness, and it's very hard to know. But they, after looking at a variety of designs, are fixed on their own pressurized water reactor, the VVR, now 1100, 1,000, 1100, 1200, and they're building for themselves and building it in China and building it in India and Bangladesh and such like. Mm-hmm. So in these other countries, I call it the East, the idea of taking a design, standardizing, getting a group of people together to learn over a long period and a number of projects and building them sequentially is a very strong idea that they absolutely believe in. Whereas you have to look at what the source of the reason why we do something different in the West. And this is true in the States, it's true in France, it's true in Finland, it's true in the UK. And it is because we believe that the most economical way to do these things is to have either completely or an element of private capital. And because the scale of these reactors is so large, and because the cost of them so large, that no private company could probably fund more than one, or maybe even one, and they definitely can't fund four, and therefore there's no incentive to learn lessons on one reactor and then go to another reactor, because there's no ability to fund these things. I mean, we've had the best example in the UK where EDF wished to build 4 big EPRs, 2 at Hinkley Point in the west of England and 2 at Sizewell, where there's an existing PWR in the east of England. And they, having signed a contract in 2012 for the electricity price with the British government, then took about 4 or 5 years to get the first project, Hinkley Point, 2 reactors, get it funded. And in the end, it got funded by guarantees from the French government and the Chinese government. Mm-hmm. And so this proves the largest nuclear utility in the world, EDF, could not finance this by itself. It needed governments, and it needed not just its own government, but the Chinese government to fund this one project. And now they're trying to get the Sizewell C, another 2 big EPRs funded, and they are struggling to get that funded. So this makes the point that our approach of having private finance involved, as it is involved in all other energy projects, but having that as a model is jars with nuclear energy, particularly at this large scale, where the amount of money that's required means you can't get private money involved. You need state money and state guarantees. And this runs counter to the idea of sequential production of the same design. You end up with different contractors and different contracts and different arrangements, mm-hmm. and different designs. Until recently, we had, in fact, we've had 3 reactors go through the licensing process in the UK. So we had the French EPR, 1600 megawatt PWR. We had the Hitachi ABWR, which went right through the safety thing, but its project couldn't be funded, so it's been cancelled, the 1400 megawatt ABWR. And we've had the Westinghouse AP1000, which has been almost completed through its safety case and was going to be built in 2 different locations, but neither of them got funded. So we see the problem, the essential problem with these large gigawatt-sized nuclear plant is they can't get funded. The economic risk is so large that no utility can afford to do it, no vendor and no consortium of banks are likely to fund these things unless there's an implicit or explicit government guarantee.
Yeah, I mean, it's very interesting. You started off with the U.S. model. I mean, I think my biases tend to be a little bit statist, particularly with looking at these successful European and East Asian buildouts, and just how essential the role of government has been, both, I think, in terms of finance, but also in terms of really picking a winner, enforcing that standardization process, whether that's through a national utility or in other means. And a big part of the case for SMRs seems to be trying to find a way for our sort of neoliberalized Western states to make nuclear viable and to make it accessible in terms of private finance, so the risk isn't too large. I have to confess to being a little bit skeptical of this, partially because I think, as you've mentioned in your paper, which we'll source in the show notes, we now have something like 50 private startups. There's lots of different design ideas, but I'm really worried, that this will replicate some of the errors that we've seen more recently, where there's been such a focus on design and not on construction experience and ease of construction, and also where, unless the state can pick a winner of one of these models and really build, a large number of them, we're never going to, get past the diseconomies of scale and take advantage of those economies of multiples. So there's kind of I think a need for humility in the West, and that's either through choosing something that we know how to do well and really trying to not just learn operationally from around the world, but what are the best practices in construction? How can we import some of that expertise? Or we need to go really small and kind of start over, because most reactor programs obviously started small and built upwards. So in that early U.S. build, I guess this would be my question. Was that also very much state stewarded in those early days, or did they really throw it away to private capital to make go, and then they, as you're mentioning, split up these companies, which created inefficiencies? Was it kind of state led, or to what degree?
So you talk about the US. In the early days, well, nearly all, I think all actually, nuclear power plant in the US have been built in states where there was a form of regulated energy market, and they used what's now become called the regulated asset base. And Vogel in Westinghouse is still trying to, or Toshiba is still trying to build in Georgia, is an example of that. So in each case, that they weren't funded. There was some involvement and some equity provided by the vendor and the utility, but the majority of it, the risk was taken by the state utility company, who said that if you build it for this amount of money, we will fund you and we'll pay you each year for the work you've done each year, and you don't have to have all this huge amount of working capital and risk. And all the reactors that were built in northeast and the southeast were all in states which were regulated. I think California in the west was also a regulated thing. So they had an implicit, not federal, but a local state guarantee, and this facilitated the early stage. But also it opened them up to a little bit of sort of local politics. We want our local contractors. We want things made in the state. We want all the jobs in the state. Very understandable. And this is part of the reason why you have so much diversity. But it did facilitate the very rapid build out in the 1970s, when the costs of the American nuclear program were not so steep. And when after 3 Mile Island, when people were modifying the designs that were going along, it led to a great divergence and diversity of these things, because the state said, we're paying, we want the rules that apply here. This design's a particular one. It has to be approved by our state safety authorities as well as the NRC. And you've got lots of local variations and such like. So the American model, several people have said, and I've never heard it countered, that no nuclear power plant has been built with wholly private capital in the world. 400 large reactors have been built. Not one has been built wholly with private capital. And plenty of economists who, and we have one very eminent in the UK, Dieter Helm at Oxford, he's absolutely clear that these large nuclear power plants will never be built with private capital unless there's an explicit or implicit government guarantee. And so, and your experience in Canada, we've not talked about that much, that it's been an explicit guarantee through your complicated Canadian way of doing things, but the Can-Do program clearly was driven by the Canadian government and then the local states and such like, and it was never a private initiative, although there might have been some private money in there in some shape or form.
And we're at times of historic low interest rates when governments are printing currency like crazy, when it seems the cost of capital is quite low. Is it just that it's a faux pas for kind of neoliberal Western states to make these kind of investments, or is it legislated? Like, why can't governments get behind nuclear anymore in the West?
Right. I think there's a problem in economics, since it's not just about nuclear; it's about all long-term infrastructure. If you do a business plan for any type of thing, you expect your future cash flows to pay for the money you invest up front. And because the money in the future is not worth as much as it is today, you've got to have larger cash flows. And this is a normal business plan and works in business, in aerospace, manufacturing, and consumer goods, where the timescales over which this is done are a few years. And you want to say, if I'm going to put this money down, I'm going to get sufficient money in the future to pay, if you like, what I put down plus the interest that I've foregone, etc. But for long-term infrastructure, and it doesn't really matter whether it's nuclear or hydroelectric or railways or roads or something, it doesn't work, because whatever the discount rate, the interest rate you have, it accumulates over a long time. So so the cash flows 20 and 30 years out have absolutely no value when you're doing the business plan. However, when you build the thing, it actually provides very good value. And this is a sort of defect about using this narrow business planning process to assess long-term infrastructure. And nuclear just falls into that because it's a long-term investment. It's always a long-term investment. Of course, a lot of these infrastructure things that I've talked about are funded by governments. Governments build roads, governments build dams, governments build bridges, governments build railways, and or they used to. I think there's a doubt about that in the US, and they would prefer to actually get those away from the federal budgets. But this didn't occur, partly because it would seem to be a national asset, and secondly because of the discount rate that federal funds tend to use is a few percent, 1 or 2 or 3%. And people say that the current interest rates allows us to do this with private money, but there still needs to be a backstop in terms of the risk, because you can only get this money we have at the moment at 1 or 2% if it seemed to be very low risk. And nuclear power plants, unless they are built identically in a sequence, then it's perceived that they are risky, because the nuclear industry, apart from places like Korea and, let's say, France, has a poor record of saying it's going to take 5 years to build and building in 5 years. They say it takes, I'm afraid we have to talk about this. I think the Finnish Olkiluoto was started in the noughties, about 2006. It was supposed to take 5 years to build. It's not yet finished. 15 years later. And the industry, this is where the industry really has to face up to the fact it's its own fault. If it goes out and says it's going to build things in 5 years, we expect it in 5 years. Maybe we'll nod if it's 6 years. If it's 15 years, it's just completely wrong. And this is a credibility problem and an economic problem, and the real reason why people won't fund things. That this is more complicated than we're saying, because in the UK, when we said we build Hinkley Point, we said it would be private capital. We'd only build nuclear if it's private capital. And so the business case for Hinkley Point was done on the basis of a discount rate of 9.25%. And this means any cash flows after about 15 years, almost infinitesimal. But that's what it was done at. And this is the return that EDF expect to get on their project. If it's late, of course, it'll be reduced. But if they build it in accordance with their plan, and it costs what they said in their plan, and the operator plan, it'll be 9%, which is actually, over long term for an infrastructure project, is a very hearty return. That people talk about, but the problem with this is, as it was pointed out by the National Audit Office, if you look at it in the UK, if you look at this from a consumer's point of view, that if they do build it on time, and it's then run for 40 or 50 or 60 years, the poor old consumer of electricity in the UK will be paying 9% a year on something which, once it's built, has almost zero risk. Right. and this is a crazy way of funding long-term infrastructure. And the National Audit Office, who are full of accountants and economists, and lay the rule down, they just said this was a failure of policy to try and fund something like this on a private and therefore a high discount rate. So they didn't offer an alternative about how to do it, but they just said this was a failure of policy. And so these things come together. We seem to have governments be able to borrow money at low coupons, and we say the business model for infrastructure projects, the way of doing it makes these things difficult. The problem is that nuclear operates in a market, and it operates against other types of generation, natural gas, wind, solar, hydroelectric, whatever, and they all have the same business plan, and particularly the newer energy sources of wind and solar are being privately funded, and it seems impossible for politicians to say, well, because this is a long-term asset, we're going to finance it in this way, right, and we're going to make sure the coupon is quite low, but we allow the renewables and solar to be privately funded. And interestingly enough, because they're now low risk, they're not paying 9%. They're getting their money at 3.5%, only 1% above the Treasury rate. Right. And so the free market has actually done a really good job, or renewables have done a very good job in free market. They've got the cost down of things, they've got the risk down associated with. It's now seen it's not as a risky investment, but an investment a pension fund wants to make, because they want to build these things and get revenue for 20 years at 3%. They're more than happy with it. This is great for pension funds. Mm-hmm, mm-hmm. And this is in the same market nuclear is competing with. I can't make money except at 9%, and it's looking for some protection which would allow it to have a coupon which is more like 3 or 4 or 5%. And this does make a huge difference to the economics of the power plant. If we just go over that at the moment, in UK pounds, the strike price for Hinkley Point was £92 a megawatt hour, so about $140 US, $135 US. That if that was financed at not 9%, but at 5%, we're talking about 60 or 65 pounds a megawatt hour, less than $100 a megawatt hour. Wow. It's dramatically different depending on how it's funded and what return is expected of it. Right. And so this is absolutely crucial to the economics. Well, there's two sides. There's two sides to the economics of nuclear. One is how you fund it, and in return, the other one is what it costs. And some people try to say we will fix all these problems by working on the funding arrangements. And other people said, no, we've got to work on the cost, because the cost is an issue as well. But there definitely is a lot of traction, a lot of scope, a lot of opportunity if in some ways the nuclear could be funded, in a lower return way.
So, Tony, I really wanted to have you on actually to speak about SMRs, because this is an area of huge experience of yours. Certainly, I love that we've laid the groundwork to understand some of the characteristics of successful builds in the past. It seems like a lot of the enthusiasm for SMRs comes out of this idea that this is something that will be amenable to our Western economic models and to private equity.
Yeah.
So let's dive into that a little bit. I don't know if you can help make the case for that. Obviously, we've had small reactors built in the past. You kind of defined some new terms: small manufactured modular reactors. We have had some hype around modularity with the AP1000, for instance, which really hasn't panned out. Maybe try and make the case for us a little bit as to your vision and how you see small modular reactors potentially working in the West.
Okay, so the thing that really shocked me when I started to look at the costs of large reactors was that about 50 people think of the costs of nuclear reactors as those fancy vessels or steam generators, or this gleaming core that goes in there, or the complicated electronics. They're very small. All the high-tech manufactured equipment, from the turbines, controls, vessel core, is about 25% of the cost. 50% of the cost is on-site labor, overheads, and construction work. And these large reactors are very complex, they're very big, but they are made by Joe Bloggs, a very skilled craftsman, with no tools and machines to help him do this thing. And because I come from aerospace, I use aerospace analogies. It's like asking a group of people to go into a field and build a 747. We've just been given a pile of equipment, not parts, but sheets of aluminium and such like, some plans, but had never built one before. And this is what building the traditional way, by what you stick built. You have large quantities of reinforcing bars and big amounts of steel, lots of concrete and such like, and groups of people who've never built one before, they do this human thing to build this thing, which is as complicated as a 747, in a field with no tools and techniques and systems behind them. This is very complicated. So we said we must try and think about this as a production engineering task. And production engineering in the last century has always meant getting stuff into a factory, getting the best tools and techniques, repeating things again and again, and the costs have fallen. So it doesn't matter whether you're making big things like steam turbines or small things like domestic cookers or cars. The story of the 20th century was getting stuff. This is Fordism, getting stuff into factories, getting some routine behind it, and having a flow of equipment, and you can get the cost to fall. And so we said, well, we can't do this with large reactors. Perhaps we can do it with small reactors. And because I come from a small reactor background, we thought we'd do the thoughted experiment. There's a barrier. We have to talk about four things. First of all, things that are smaller intrinsically cost a bit more. It's called the diseconomies of small scale, or the economies of large scale. It's to do with, if you make a vessel that is twice the volume, it doesn't cost twice as much to make it. It costs about 60% more to make it. And if you come down smaller, you have the diseconomies of scale. So if you're going to do small things, and this is absolutely played out by what we've seen in nuclear reactors in the last 40 years. Every vendor has tried to solve economic problems by making the same design they had, but a bit bigger. So in the 1970s, we had 300 megawatt reactors. They became 600 megawatt. They were 900, 1200. We're now building 1500 megawatts. Every time people have made bigger ones. Actually, it's not yielded the value that they thought, but I was saying, if we go back to these small reactors, we do know there's this literature around and evidence around the diseconomy scale. So we have to offset that. And what are the means of offsetting it? Well, the three that the work we did and we investigated, and we tried to see how they were affected by the size of the unit we built. You know, what's the spectrum between a 100 megawatt reactor and a 1,000 megawatt reactor, and how these factors of scaling and the cost, the production engineering play out. So the first one is standardization. So instead of designing every plant as a unique plant and therefore incurring lots of on-site design costs and then regulatory costs and such like, let's design it once like we do in factories. And so it's standardization. And standardization is a cost reduction thing by itself, but it's also key to the second one, which is modularization. Modularization is a way of taking bits of the plant that you can transport to site, and instead of manufacturing it on site, you can assemble it on site and you manufacture it in a factory. If you can manufacture it in a factory, you have the tools and techniques and cranes and robots and whatever else you need around you. And also you can repeatedly make these things for a number of customers in your factory, and the teams can learn how to make them better. So modularization depends on standardization. You get better productivity because you have better access and you have the tools to set things up, much higher productivity. And this leads on to the third thing.
Just to be clear, in terms of the modularity, currently reactor vessels, steam generators, a lot of the valving, pumps, yes, that's all being made in factories. But yes, are you talking about the other components, like yes, the concrete that's being put down, making that modular? Like what's new about this modularity and manufacturing in a factory? Yep. Is it different parts that we're doing, or?
So we're talking about, well, what we're investigating is, could we modularize the whole of the plant? Probably not. What could we modularize? What commodities could we modularize? What steel work? What reinforcing cages? What concrete work? What other types of equipment? What instrumentation cables and power cables? How could you fit things out and assemble them as units? And because these current designs are largely made of reinforced concrete, this is much more challenging, although there's some good work being done by people looking at modularization in civil engineering. And in other sectors, there's quite a drive to modularize buildings and railway components and parts of water treatment plants and such like. So there is a background of R&D into modularizing some of these other commodities. And as we've said before, a lot of the steel work, there's a very good example of modularizing steel work from shipyards, where ships used to be built from uniquely on a ship, on a slip, with people turning up with plates of steel and laying them out and riveting them in the 30s and welding them later on them. Nowadays, they're built in shops and modules, huge modules weighing 10,000 tons, lifted in place, and they fit to quarters of an inch and then welded up. And these modules are actually fitted out with a lot of cabling and painted and internal things before they're transported to site. And so this idea that you can fit out a large steel structure is a matter of fact and routine in shipyards. And so we're talking about what scale we can go through the whole of reactor plant. So what we did was we took a piece of work that had been done actually quite a long time by Stern and Webster, where they looked at the modularization of a 3-loop 800 megawatt power plant. And we took this and we said, how could this be applied if it was somewhat smaller or a lot smaller? How would this facilitate the modularization and movement of this work to factories? And the constraint there is, how do you transport it? Mm-hmm. In UK and Europe, you won't get it down many rail lines because they're bendy and the tunnels are quite small, so it's down roads. Roads are reasonably wide, but they tend to have bridges which are a certain height, and these provide an envelope about what is allowed to be transported. So one of the researchers, Clara Lloyd, looked at the issue of modularization. Taking this design, how could you chop it up into pieces what number of pieces you require, how could you transport them, and what would be the trade-offs with the economics of moving this away from site and doing assembly on site to doing manufacturing in factories. And what we found was you have to be quite ambitious in the degree of modularization, and it's easier to be ambitious in what you can do. You can't do everything, but what you can do, we see we need about 2/3 of the equipment that's normally made on site, we need to modularize. To achieve that, it's much easier to achieve at a smaller size of reactor. And so we see the degree of modularization becomes larger the smaller the reactor. But remember that the effect of diseconomies of scale becomes more adverse as you come to small reactors. So there's a trade-off here between small reactors which cost more and being able to modularize more of it because they're actually physically smaller reactors. And so her piece of work was really, one element of it was at that test. But we are talking about, and she really demonstrated that you do need to be very ambitious. So if you take the stuff that's already made in factories, the turbines and the vessels and the instrumentation and such like on one side, the rest of the plant, you need to be able to modularize about 2/3 of it. And this is very challenging. And this is the main area of work. If you can modularize it, then the productivity improvements you get in the factory are significant. And also because you can then have a factory which is repeatedly making these things for a number of customers, you can get production learning over a large program. So the keys to this concept are standardization, high degrees of modularization, and quite a large program where we're saying perhaps 10 gigawatts of nuclear power needs to be of a standard design to be able to get to the sort of costs that the target costs we're going to be. And what we found was that somewhere in the region of about 300 megawatts seemed to be a sweet spot between any lower than that the diseconomies of scale work against you, and any larger than that, the inability to modularize these things would be sort of impeding the way forward.
I mean, in a context of at least 50 startups working on a variety of advanced and small modular concepts, the idea that we need to order at least 10 gigawatts of a single design, standardize it, create the manufacturing facilities. I mean, first off, there's going to be a big first of a kind cost to getting this whole factory infrastructure built up. And then secondarily, someone needs to pick the winner and order 10 gigawatts of nuclear. I mean, and I know we're trying to sort of use this model to make it amenable to private capital and make it work in the West. I mean, how realistic do you think that is?
Well, I think that 10 gigawatts is a lot, and particularly when you put it in pounds or dollars terms, whichever way you do it, it's a lot of money. But the French built over 50 gigawatts of plant in 13 years with these 900 and 1200 things. The Koreans over the last 20 years have built about 20 gigawatts of this system 80 design. The Chinese clearly are well on the way. They built 25 gigawatts of a rather similar plant, and they're planning 100 gigawatts. So these centrally planned economies, if you include France as a centrally planned economy, this was the will of de Gaulle, carried on by subsequent presidents, that it is possible to there is the scale of the need is definitely in these large numbers. I think there's sort of no way around this. Let me use another analogy, because in nuclear we're very much entrenched. So if you build a large civil airliner like the 777, that you need so many orders before you launch the project. You'll do some preliminary works, but you'll not cut metal and you'll not launch them, you'll not sell any unless you've got a decent number of orders. And that number of orders is probably 300.
Yeah.
they cost $100 million each, $330 billion as a sort of round number. Boeing, with all the experience, will not launch a project unless he has that number of orders. He wants to sell perhaps 5 or 6 times that, but unless he's got that orders, he will not launch it. It is not possible. And same is true of Airbus. And this is the same is true at a lower level when you talk about if you launch a new car, people know they want to sell 500,000 of this car. They convince themselves they are. And because they've done it before, they can do that. The problem is that we don't have this track record in nuclear, but we need to think about it in this way. If we're going to production engineer things, we have to think about them, unless there's some minimum order size, that it's not possible. Now, it is a big hill to climb, and we've been looking at that in the context of the UK. That I don't think the UK market's big enough to support 10 gigawatts of a particular design, and not the political work, but perhaps by building 5 gigawatts of a common design and 5 gigawatts exported from a single factory, then this is possible. And so for a small country, a smallish country like the UK, I think export's an essential part of this, and it becomes feasible. And you say, well, 5 gigawatts UK, that's a lot, but Hinkley Point is 3.3 gigawatts. It's just 2 reactors. So it's not out of kilter that, first of all, the demand for the power there, it's a different type of program, but 5 gigawatts is not out of kilter with the sort of size of market in the UK. And of course, in the US, there's 100 gigawatts of nuclear power. A lot of it's been life extended. At the moment, it's not very economic to build nuclear power in the US. But sooner or later, if the US is still going to have 20% of its power from nuclear, it's going to have to build 100 gigawatts of something or other. I just wanted to dive off related, because you keep saying that, well, there's lots of designs of SMRs around. There's really 2 groups of SMRs. There's those built based on light water reactor technology, which are not innovative in their technology, and this includes there's a GE BWR small reactor, and there's several PWRs. The technology of building them, the technology of operating, the technology of the fuel, the technology of the safety is well understood. People have really worked at this over 40 years. What we're talking about is innovation in the way it's financed, in the way it's organized, in the way it's made. There's another group of reactors around which are offering a different way of getting to low cost. And those are, we call them advanced modular reactors in the UK. And they're generally small, so gas-cooled reactors, fast reactors, molten salt reactors and such like. And there, as you say, there's a proliferation of those designs around. And if people want to focus on going ahead on these, they're going to have to pick winners, because there's so many different designs. I mean, I think there's 2 or 3 gas reactors just in Canada with a Canadian badge on it. And of course, in America, there's lots of designs. And even in the UK, we've got a molten salt reactor and a small gas reactor as concepts which people are plugging. And but all of those advanced modular reactors have to go through either technology proving or a prototyping stage before you can commit to building them in series. Their basic approach is, because they, in some cases, are low pressure, or in other cases have a lower power density, they're saying they're intrinsically safer and therefore don't need the complex safety systems that light water reactors require. And because they don't need this extra kit, this extra safety kit, which sits around, is protecting against the very unlikely event, but it has to be there and has to be maintained and has to be at a high standard and such like. And this adds to the complexity. Because they think they're inherently simpler plants, because of a simpler safety case, they need less kit to build. And that's their basic argument. And it may well be true, but I don't think we know at the moment. Mm-hmm. But I think I just wanted to say that there's a parting of the ways between. There's 2 completely different concepts about how to get to low cost.
Right. No, for sure. I mean, I've posed this before as a question. I think it was Jack Devaney of Thorcon. We have ITER for fusion, but it really seems if we want to get nuclear right, that we need to get a large number of countries and industries together to pick a couple of advanced designs and really
Yes.
work those out, and again, find ways to pick a winner, standardize, and get going from there. But from what you're saying, these PWR designs are much more ready to go because we don't need to do all sorts of new materials testing or fuels testing. We're kind of ready to go there. Yeah.
Yes. But they've got their own challenges in this production engineering approach, which is new to the industry. And it is quite challenging because most people in the industry have been brought up on building gigawatt-sized reactors one at a time. It's quite deep in the psyche in the industry. So the completely different challenges. The challenges with small modular light water reactors are in the project orientation, the production management, which is almost an anathema in the nuclear industry. And on the advanced modular reactors, the challenge is that there's just they've all got some technological uncertainty, and we need to build something, and that's going to be quite expensive. And really, the winners will be the ones who can get funded by some government or other to build a demonstration gas-cooled reactor or molten salt reactor or whatever.
Yeah, it's interesting. I was speaking with François Perchet, he graduated and entered the nuclear workforce in France as an engineer in, I think, 1977. So he was sort of, his whole professional career was that amazing French nuclear build-out on the Mesmer plan. We'll be releasing that episode in a couple of weeks, but he was really talking about all the preconditions that were there in terms of the amount of research that had been done. I mean, you have Henri Becquerel, the Curies laying the foundation for the science, but post-war real reconstruction efforts, huge industrialization, heavy forging industries. And in the context of having deindustrialized so much as part of this sort of neoliberal revolution, it strikes me as, I try and be optimistic and hopeful, but I'm very worried for the nuclear sector in the West, given the way that it's just sort of been carved out, our whole industrial capacity that we'll be able to do this. It's going to really take significant government leadership and dedication to, just bring some of the manufacturing home, for instance. I know Canada is being positioned very much as a potential leader because I think we have a more refined regulatory environment. So it's brought a lot of SMR interest here.
Yes.
In terms of, what's happening so far, I mean, China's, I think, they've poured their base mat for the CP100. Obviously, Russia's built a few floating SMRs, the academic Lomonosov, if I'm saying that correctly. Are there any hints of SMRs starting to work? And a big question of mine is, if this model is a potential panacea, why aren't we seeing more of it coming out of like established nuclear vendors, as in China? Or is it just the beginning? Tell us about sort of what's happening right now, because it's always good to see, real world evidence rather than just modeling.
So let's just deal with the Russian and Chinese ones for slightly different reasons, which are matters of state. I think both Russia and China are building small reactors. Russia's built one, and they wanted to provide power in Siberia, and that actually to help them power their gas pipelines. And there wasn't not many options, and the price of bringing diesel in to run diesel power was just so high. And what they've done is they've taken some reactors which they designed and built and used in their nuclear icebreakers, and they put them on a barge and they put them around that. This is very much, and they're going to build another one, I'm told. So this is very much using something which is in their kit bag of military-derived nuclear reactors, small reactors, and a particular need in Siberia for point power. And this model, of course, have been picked up by some Canadians who say we've got the same problem in some of the far distant places. We have no other way of making power, so let's have a small reactor. The Chinese are taking a reactor, which I understand comes from one of their aircraft carrier designs, and they have a particular need for power in the disputed islands in the China Sea, and they are building one on land to prove it works, and then we would expect them to build one of these things on these islands. And I'm sure there'll be some fun and games around that. So that they have particular matters of state about why they want to build an SMR. I don't see this much demand or push in China for a proliferation of their SMRs. Their 1 gigawatt power unit, the Huliang Wang building at the moment, is the right sort of size for their grids. They've got huge demand for electricity. In fact, although they've got the biggest nuclear program in the world, they're sticking at, because they're expanding their electricity sector so large, only about a couple of % of it is nuclear, and looks like that'll be in the future, even with the quite high build rate. So I don't think Russia is building large reactors. China building large reactors. They'll continue to do that. They happen to have built some small reactors. I don't think they are doing this for economic reasons. The things that are going around there's at least three sort of tangible projects that are going on. First of all, the Koreans, almost as an exercise, designed a small reactor, 100 megawatt PWR, integral PWR, and they are apparently going to build one of these in Saudi Arabia with the with the government there. Perhaps more as a demonstration of technology, but it's perhaps a little bit small, but it's a possibility, and that they have got the industry and they have got the infrastructure to be able to build this if they were serious. And of course, they know how to build reactors quite cheaply. I think it may be more of an exercise because they've already built 4 large PWRs in the United Arab Emirates, and their aim is to sell another 10 of those to the Saudi Arabians, or 20, or whatever it is, and therefore having some sort of industrial link. So there's at least a couple of reasons for the Koreans to be building a SMR in Saudi Arabia. They may decide they want to commercialize it and sell it elsewhere. I don't know. But while they are selling their large reactor, this is one of the problems of existing vendors. If you've got a large reactor design and you're selling it, why would you try and put your large reactor business out of business and take a risk with a small reactor? Right. And I think this is the Westinghouse problem. Westinghouse have designed several times small reactors. They built designed a thing called SIR, 300 megawatt, and tried to say that was competitive with the AP1000, but it's a good piece of work done 10 years ago on that. And they couldn't convince themselves it was economic. But they were trying to sell AP1000, so there's a lot of people inside Westinghouse who said, well, why would we want this to be economic? And then more recently designed a 225, slightly different arrangement reactor, but they couldn't convince themselves that was competitive. So the two things which I think are more active is General Electric with Hitachi are downsizing their existing BWR to 300 megawatts. They say, well, in Japan, the size of the reactor they've got suits their grid, but they're probably not going to be allowed to build anymore. So they have a need to have a new product. And a smaller reactor is attractive to some countries, and it's been actively marketed in Eastern Europe, Poland, Lithuania, and such like, as a way of countries that don't have nuclear getting into it without exorbitant costs. And it has a head of steam behind it, and I think it's now going through some safety regulation. And in the UK, Rolls Royce, with a consortium of other companies that have designed a 400 megawatt, pretty conventional PWR, and they have some of the ideas we've just been discussing close to what they're trying to do, and they are actively marketing in the UK and abroad. And I think they're just about to get the next tranche of funding. They have some government support for this. But we'll see if this gets launched. It will get launched with an order of, I don't know, 20 or 30 reactors, 10 from the UK and 10 from abroad, because Rolls Royce as a private company is not going to take this sort of risk unless it's got a good order book, and all the complexities of setting this new arrangement up can be foreseen to be paid for. Mm-hmm. So I think those two slightly different projects are the most nascent ones. There are particular ones. There's a very small reactor being built, or an SMR water-based SMR being built in Argentina, but this is just the size of reactor that they feel they can afford and build, and it happens to be a light water reactor. It happens to be an SMR. I don't think it's production engineered, and I don't think they intend to export it. And there've been some other studies in other parts of the world where people have said, well, for our grid, a 300 megawatt reactor is probably the right size, so we'll go and do some design studies around it. But I don't think they don't have any big funding or big industrial muscle behind them.
Just maybe to close off, so in Canada, our nuclear plan, it's sort of threefold. There's this idea of micro modular reactors for the north, some burner breeder technology in the east, and a commitment to SMRs for our broader decarbonization strategy. Leaving aside those first two programs, the decarbonization strategy involves building a 300 megawatt, probably the GE Hitachi BWR, building a kind of example project in Ontario, and then building several more in one of our very coal-heavy provinces out in Saskatchewan. It looks like the initial investment in getting this kind of a project going, getting the factories tooled up, et cetera, is going to mean that the first several reactors are very expensive. And until you have those orders in place and you have a number built early on, you're going to really see these diseconomies of scale and these first of a kind costs. I'm kind of worried that that's going to really scare government and private business off of this strategy once they see the first few being quite expensive and perhaps not delivering on that value that you'd get after a long-term commitment. And again, in the West, with our sort of 4 or 5 year election cycles, that's another risk that comes into a mega project like this. I mean, is the solution to that really, again, some kind of international cooperation between a bunch of countries in the West to make this happen? Like, I'm just trying to see what are the realistic preconditions that are required to really make this work. And I know that's kind of the last I think try and wrap up in about 5 minutes, but yeah.
Yeah, so the points you made are very good ones. And I think you're absolutely right at the bottom about that. The costs of setting these things up are high. They're high, particularly for a private company, but they're not high for a government. So we did some. One of the other students who work in Probably Lions looked at this issue, and using data from MIT for the cost of doing development and the safety case and the factory side of things and the uncertainty about the first reactor and such like. The additional development costs, broadly development costs, the costs before you get into repeated manufacture, were about $3 billion. And all that seems a lot of money. Over a 10 gigawatt program, they represent what I would call a design uplift cost of about 7% on all the reactors. So if you can conceive of things as a 10 gigawatt program, just like getting back to my 777 costs about $10 or $15 billion to develop. They amortize that over the airliners. They're used to the production learning. They're probably the first few they probably make a loss on. If we can think in this way, this is exactly the way that big capital goods are financed and done. Again, the question is the credibility about the price you're going to get to, the credibility about the build schedule, the credibility about the learner. And these are production engineering things. And this is really what the development program is about. It's about proving these things. And so to get back to the money. So if you talk about $3 billion, if that's the right number, for a company like GE or Rolls Royce, that's a lot of money, to find this against a new product for a market that's little uncertain. This is a lot of money. For a government, it's not a lot of money, or for a program, it's a lot of money. And so it's a matter of how this is thought about and how it's conceived. But the upfront money about doing these things in a different way is an impediment for the industry. Let me just make one other point. If you talk to people about something like AP1000, how much money did they spend on AP1000 on design before they launched it? About $300 million. So about a tenth of this number. And the norm is we'll do all this fancy development stuff about the features, we'll design the vessels and such like, and we'll put a sketch about the whole thing. We'll spend a lot of money with the NRC getting a rubber stamp, and then we'll give this to someone to make $300 million. We're talking about $3 billion. The upfront money with this concept is about 10 times what it would be for a large reactor. And that is a real impediment to anyone in the industry at the moment.
And that $3 billion, to be clear, is because in addition to the designs, you are building the infrastructure, the factories to build these modules,
and development work to prove the programs can be shot, to prove that the learner, to get the equipment together, to prove that you're going to get the cost reduction. This is all about putting money into development before you start building, and building a supply chain capability to deliver these things. And the factory is people talk about the factory. It won't be one factory, it'll be several factories. But the factory itself, putting a factory up is not expensive. It's what goes in it and the intellectual capital that's captured by putting this equipment that's designed through a factory system. That's what costs the money, and that's what is valuable.
I guess the challenge with the airline analogy is that airliners are a very proven technology.
Yes,
it's a growing sector. We need more airlines. We don't have an alternative to the jet plane for commercial transport. So big challenges ahead. Very humbling. Tony, it's a real pleasure to have you on. I've learned a lot from this conversation. I think I'm going to try and sneak you back into the guest list here, because there's a lot more we could chat about, I'm sure. But thanks again for making the time to come on Decouple.
Thank you. It was fun. Thank you.